Why do we need to achieve a 1 millisecond delay?
As a human being, when we interact with our environment, we try to catch some object, whatever all, we actually want to see the object and with a 1 millisecond latency. If the latency is more than 1 millisecond, we're not going to be able to catch a ball. We're not going to be able to interact with our environment. So our whole natural interaction with our environment is at a millisecond speed. So if we want to control real and virtual objects of our real environment, we have to get latencies down to 1 millisecond.
And what are your 5G research tracks in this sense?
At 5G Lab Germany, we have 4 research tracks because we think that to achieve the tactile internet, the 1 millisecond, we need to be able to do the next generation wireless air interface as well as the network. The second track is we have to be able to design the right silicon systems because we're talking about millimeter wave silicon systems, very low latency silicon systems, highly resilient, etc. The third part is we have to make sure that the cloud that is running the control application moves as close to the edge as possible, mobile edge cloud. So we're looking at how to build a mobile edge cloud. And the fourth track, finally, is obviously looking at the different tactile internet applications because it only is reasonable to spec the system according to what is needed. And for that, we really have to check out some of these applications to make sure that we don't over-design the system.
And what are the spectrum implications?
The spectrum implications are such that we have to move to higher frequencies. Obviously, on the one hand, the 6 to 15 gigahertz range is great because we have very nice propagation still. But we also, as we found out, have very good propagation at frequencies above 100 gigahertz. So our way of looking at it is there's a sort of a valley of trouble, or sometimes also called a valley of death, in the frequency range around 30 gigahertz, where we need a lot of antenna gain for these millimeter wave ranges, but we have difficulty building the systems. The large antenna arrays become very complex and costly and expensive, whereas at very high frequencies, it turns out we have fairly good propagation and we can build compact systems so that we can actually, in the end, build low-cost devices.
And how about the energy in these higher frequencies?
The energy consumption is a problem in these higher frequencies. There are 2 problems. First of all, independent of the high frequency, at high data rates, we have a high bandwidth, so our AD converter and DA converter consumes a lot of energy. So building an 8-bit AD converter or 10-bit AD converter is not possible. We have to go down to systems with 1-bit, possibly 1 single bit AD conversion, which means we have a wireless channel now where we have to check out how to modulate and demodulate over channel, not only the radio part, but also the AD-DA converter bottleneck. And the second part that we have to look at, obviously, is the power amplifier, because we get efficiencies of like 7% or something like that at these high frequencies. But this is only true like if we want to do OFDM with a high peak to average power ratio. If we build a constant modulus signal, like we used to do in GSM, GMSK, then we can actually get the efficiency up in the 20% range and even higher. So, and then, by the way, it turns out we only need a 1-bit ADC. So we have done both in one way. So if we go to constant modulus kind of systems are similar, very low resolution systems that require very low resolution in the amplitude, we can address both simultaneously, PA problem and the AD converter problem.